An introduction to systems of linear equations. Solution sets to linear equations in n variables. Keep in mind that a prerequisite for studying linear algebra is that you've already passed basic algebra. So that's algebra 1 and 2, or intermediate algebra, college algebra, and so forth. Therefore, you should be familiar with the slope-intercept form of a linear equation, which is in two variables, so y equals mx plus b, or of course the standard form of an equation ax plus by equals c. In linear algebra, we're going to be focused more on the standard form, but because we're dealing most often with more than just two variables, instead of using x, y, z, or w, x, y, z, and so forth, we just use x with a subscript. And the coefficient, we would just use a as a subscript. So a1, x1, which could be like 2x1 plus 3x2 equals 7. So again, very similar to the standard form, using x1, x2, x3 instead of x, y, z. Again, for more than two variables, we would just continue that pattern, a1, x1, a2, x2, an, xn, and so forth equals some real number b. Now we want to take a look at how to find a solution to a linear equation in n variables. And what's one thing new that we're going to look at, and possibly you've studied this before in Calculus 2 or 3, but if you haven't, don't worry. We're actually going to solve this parametrically, which means we're going to solve based on some other parameter. So before we do parametrically, let's just look at how we might solve this normally. So normally we would just say, oh, let's make an XY table, and then we can plot a graph that has all of the points on it. And that's okay, and that's kind of what we're going to do now, but what we're going to do is we're actually going to set x equal to some expression based on the parameter of t. So we're going to make t our parameter. And that just is going to be it's just basically another variable that changes. So we can set some limits to our parameter, an upper bound, a lower bound, and so forth. But everything is now going to be based on t. So to get x by itself, I'm just going to do some normal algebraic manipulation. I get x is equal to 10 minus 5y. And y is then going to be my free variable. So think about the independent, dependent variables. We're saying y is independent and x is dependent on y. But now we're going to write this parametrically. So we're going to say let y equals t. T is the parameter. And so t is going to be whatever, y is going to be whatever we set for t. And x is going to be 10 minus 5t. So again, this is the correct solution. The graph doesn't change, but it would be based on the value of t. So here, this ordered pair is still the point 0 on the x, 2 on the y, but that means it's also where t is equal to 2. So that's how we would find that, is using the parameter of t. It's still going to give us the same graph, but solving parametrically is going to be something that we do quite often. Let's go back to the topic of free variable. So keep in mind that it would be possible in this case, because you might be asking yourself that question, why did she choose x? Well, I could have said let 5y equal 10 minus x. Therefore, y by division by 5 would be 2 minus x over 5, or 1/5 x. And then x would be a free variable. Would that be the exact same thing? And the answer is yes. Typically, we're going to use whatever free variable is easiest to find. And typically it's going to not be the x variable that is free, but you'll see as we work more and more with parametric equations and with linear systems, exactly what a free variable can do for us. Now that we understand how to find a parametric representation, let's do so for an equation involving three variables. Now keep in mind, I could have just as easily written this as 3x1, 4x2 minus 1x3 equals 12, and we would be doing this exactly the same way. So how am I going to solve this? Well, I'm going to start by getting a variable by itself. So let's isolate 3x. 3x is equal to 12 minus 4y plus z. So I've just shifted the 4y and the z to the opposite side, of course changing the signs. Then I'm going to divide everything by 3. So 12 divided by 3 is 4. Then I get 4/3 y, and I get 1/3 z. So what's my parametric solution? That x is equal to 4 minus 4/3 s. So we're now going to use s and t because y and z are both going to be our free variables. So 4/3 s, 1/3 t, where y is equal to s and z is equal to t. This is my parametric solution. Two free variables, x is reliant upon the value of those free variables. It also asks us to then give two particular solutions. So that's the very easy part. If we need a particular solution, essentially I'm just going to assign a value for s and assign a value for t, which is our two free variables, s and t. And then I'm going to find x based on that. So I'm going to say x is equal to 4 minus 4/3 times 0 plus 1/3 times 0. So I'm just using this equation and replacing with 0, s and t. And that would just give me 4. So one solution would be x is 4, y is 0, z is 0. And another solution I can find the same way. So I'm going to let s equals 3 and t equals 0. So x is equal to 4 minus 4/3 times 3 plus 1/3 times 0, which gives me 4 minus 4/3 times 3 is 4, which is, and then minus 0, which is 0. So another solution would be 0 for x, 3 for y, and 0 for z. Now the last question says, what's the geometric representation of this solution set? Hopefully we know, because we have 1, 2, 3 variables. Our geometric representation would be a plane in 3 dimensions using the x, y, and z axes. Now it's no fun just to talk about one linear equation, so let's talk about a system of linear equations, because that's where all the fun happens. Now I'm going to be using just a set of 2 linear equations and 2 variables to demonstrate what our possibilities are. Obviously, as we study more into linear algebra, you will be having more variables, more equations, and so forth. But for now, it's important to understand the basics. What are the possibilities when you have a system of linear equations? You can either have one solution. So here, let's say I was solving this by adding together 2x plus y minus y gives me 0, 3 plus -1 gives me 2, so I get x equals 1, and then I would plug 1 back in to say 1 plus y equals 3, so y must be 2, so my solution is 1, 2. That's what happens when I get one solution. They can cross at exactly one point. Now I could do the same thing with the next equation, but hopefully I can see that if I took the first equation by 2, I would actually have the exact same thing as the second equation. So my first possibility is that I have just one solution. My second possibility is that I have the same exact equation 2 times, which means everywhere the first equation happens, the second equation also happens, so it's really 2 lines on top of one another. So I'm going to have as many solutions as there are points on the line, which is an infinite number. And for my last one, let's say I subtract these equations. X minus x gives me 0, negative y plus negative y, minus negative y gives me 0, and 3 minus negative 2 gives me 5. Well, that doesn't work, right? 0 can never equal 5. So if I get an equation like that, I can see that these two are parallel. Are these ever going to touch each other? No, because they're parallel and will be until eternity. So we can either have a consistent one solution equation, consistent infinitely many solutions system, or an inconsistent no solution system. So notice if we do have a solution, it's considered consistent, and if you don't have a solution, it's considered inconsistent. There are 2 ways to have a consistent system. You can have just one solution, where that one point where 2 lines or 3 lines or 4 lines or so on meet, or 2 planes and 3 planes and so on. Or you can have infinitely many solutions if all of the lines or planes are exactly the same. Or you can have an inconsistent system with no solution. Solving a system of linear equations using back substitution. Before enrolling in a linear algebra course, you would have already taken Algebra 1 and 2, which is equivalent to intermediate and college algebra, which means you should be familiar with solving a system of equations using substitution, elimination, or graphing. If not, I will link a video in the comments that takes you back through how to perform those steps or solve using those methods. Right now, we are going to fall back on those methods using back substitution in something called row echelon form. So row echelon form is something you're going to hear quite often. And in row echelon form, you're going to have this stair-step pattern where the leading coefficient or the first coefficient in each line is a 1. And the first or top equation has the most variables. The equation just below that has 1 fewer variables, so notice this one does not have an x. The one below that has 2 fewer variables, and so forth, all the way down to where we have just one of the last variable. So this is row echelon form, and we will talk about it in a little more detail in the next part of this video. But let's just remind ourselves how to solve this equation. And when we are using back substitution, which is the method that we will use for now in row echelon form, we already know that we're going to have 3 solutions because we have 3 variables. So we're going to have a solution for x and for y and for z, or of course we could have no solution or infinitely many. But in this case, because I know z is 3, I don't have to work very hard to find z because it's found for me. I do want you to notice again that this is row echelon form because there is a coefficient of 1 in front of x and y. So next I'm going to solve for y. So I don't have to solve for z, but I do have to solve for y. The equation that includes y and z is y minus 4z is equal to 4. And because I already know z is 3, I'm going to replace z with 3. And I get y minus 12 is equal to 4, so y is equal to 16 by adding 12 to each side. And then I will finish by solving for solving for x. I already know z is 3. And I will solve for x using the first equation. So x minus 2y plus z is equal to 0. I'm going to replace y with 16 and z with 3. That gives me x minus 32 plus 3 is equal to 0. X minus 29 is equal to 0. So x must be 29. So my solution to this system is 29, 16, 3. Again, this is using back substitution because we already have one solution. We go back one to find the next solution, and then we go back one to find the initial solution. Here's a question for you to try on your own. Again, it's already in row echelon form, so press pause, try this question on your own. When you're ready, press play to see how you did. So to begin, we can see it is in row echelon form. Those leading coefficients are 1. We have that stair-step pattern that we're used to. And we know that we're going to have 3 solutions, one for x, one for y, one for z. And then we already know that z is 2 because it's given to us in the last equation. So my first step is to then solve for y, which means I'm going to use that second equation that it contains just 2 variables. Y plus 3z is equal to 5, and then I'm going to replace z with 2. And that gives me y plus 6 is equal to 5. Subtracting 6 from each side gives me y is equal to -1. And then I'm going to solve for x, which means now I'm going to use that first equation, x minus 2y plus 3z is equal to 9. I'm going to replace y with -1 and z with 2. So I have x plus 2 plus 6 is equal to 9, or x plus 8 is equal to 9. By subtracting 8 from each side, I get x is equal to 1. So my ordered triple, or my solution to this system, is 1, -1, 2. Using Gaussian elimination to rewrite a system in row echelon form. We have spoken about row echelon form, but have not given it an official definition. So let's ensure we understand row echelon form before we begin rewriting equations in that form. For a system of equations to be in row echelon form, that must have the following properties. 1, any rows consisting entirely of zeros occur at the end of the system. 2, for each row that does not consist entirely of zeros, the first non-zero entry is a 1, which means a leading coefficient of 1. And 3, for 2 successive non-zero rows, the leading one in the higher row is further to the left than the leading one in the lower row. So I have 3 systems of equations, and we're going to determine if any of them are in row echelon form or how we could turn them into row echelon form. For system number 1, we can see I have 3 equations, and they do all have a leading coefficient of 1, so it fits number 2. If we have any 0 rows, we don't see them, so it fits the first criteria. But for 3, it says for 2 successive non-zero rows, the leading one in the higher row is further to the left. I can see that these 2 equations violate that. The leading one in row 3 is further to the left than in row 2. So I could rewrite this in row echelon form by simply swapping those 2 rows. So this is a no, but we can change it into row echelon form by swapping row 2 and row 3. What about system 2? System 2 doesn't appear to have any all 0 rows, though we can't really tell in equation form. But it violates number 2 that says the first non-zero entry has to be a 1. So we can see that the first non-zero entry of our row 1 is a 4. The other 2 have a leading coefficient of 1. So this is a no, but could I switch it into row echelon form? Yes, I could divide everything by 4 to make this x minus 2x plus 3x equals 9. So no, but it could be changed easily. And finally, let's look at number 3. Number 3, any rows consisting entirely of zeros occur at the end of the system. We're not well versed enough to know that there would be a non-zero row here, but likely there were 3 equations and the y eliminated at some point, and that would give me a 0 equals 0 row down here at the bottom. So yes, it fits number 1. Number 2, for each row that does not consist entirely of zeros, the first non-zero entry is 1. We have a 1 and a 1, so it fits that criteria. For 2 successive non-zero rows, the leading one in the higher row is further to the left than the leading one in the lower row. Absolutely. So yes, number 3 is in row echelon form. In the process of rewriting a system of equations in row echelon form, we are allowed 3 row operations, sometimes called elementary row operations. And the first of those is interchange. And interchange is where I'm simply swapping the location of 2 equations. Now, when we're doing this, we are identifying these by rows. Row 1, row 2, row 3. So what I want to do in my first equation is I see that z equals 5 is my first equation, but I would like it to be my third equation. So for my row operation, I want to interchange row 1 and row 3 so that z equals 5 will be the third equation. To show that, I'm going to have R1, and then this is the equal sign with the arrow on each end, R3. That tells me I'm interchanging row 1 with row 3. My new system of equations has row 3 first. Nothing happened to row 2. And row 1 is now row 3. That is the interchange row operation. Now let's take a look at scaling. Scaling is where we multiply an equation by a non-zero constant. And quite often in scaling, we'll be multiplying by a fraction because division is not allowed. So for instance, in my second system of equations, we can see that my second row all have a common factor of 2. So I can simply rewrite row 2. Again, this is row 1, row 2, row 3. So I'm going to rewrite row 2 by dividing everything by 2. But again, I can't divide. So I'm just going to write 1/2 row 2 is my new row 2. So that's how we're going to show that it's a scaling operation. So nothing happened to the first equation. My second equation is now -2, and honestly, I would probably do -1/2 because we always like those leading coefficients to be positive. So this would be positive 2x, and then positive y, and minus 2z is equal to -8. And nothing happened to that third equation. And finally, we have replacement. Replacement is by far the most common row operation, and that's where we're adding a multiple of one equation to another. So for instance, in my third system of equations, I can see that z equals 5 is exactly where I want it. But remember, in row echelon form, I don't want there to be an x in the second row. So I'm going to use replacement to say, if I took the first row and I made everything the opposite sign, negative, negative, positive, negative, and then I added it to the second row, we can see that negative x and positive x would cancel, and that's exactly what I want. So I would say negative row 1 plus row 2 is my new row 2. Now, why do I want it to be row 2? Because I want there to be an x in that first row. I don't want there to be an x in the second row. So I'm going to replace row 2 with the sum of negative row 1 and row 2. So again, think about all of these as negative. But when I'm rewriting row 1, I want you to notice row 1 isn't getting replaced. So the original row 1 of x plus y minus z is equal to 2 is still row 1, but when I'm adding it to row 2, I'm just going to negate it for a moment. So that gives me 0x, and negative y and minus y gives me minus 2y, plus z and plus z gives me plus 2z, and then negative 2 plus 16 is 14, and nothing happened to row 3. So those are the 3 row operations. Now that we understand row echelon form and the 3 row operations, let's take a look at how to rewrite these systems in row echelon form. So we've got some basic steps, 4 basic steps that you're going to use. And again, depending on when we're asked to stop, this one says to rewrite in row echelon form. So it might be that we don't have to continue to solve the system. We're just rewriting it in row echelon form. But for good practice, we're going to do all 4 steps. We also have some optional steps. So these are steps that you may need to do in order to rewrite this in row echelon form. Don't worry, we're going to kind of go through those steps as we go. The first step is to eliminate the x variable in equation 2. So you'll remember row echelon form is that stair-step pattern. So I want to get rid of this x. And in order to do that, I'm often going to use row 1 and row 2. So I want to think about what would I add to row 2 to get rid of the x? Well, I would need a negative x. So how do I make a negative x? I'm going to have to think about row 1 as negative row 1. So again, how would I write that? I'm going to take negative row 1 and add it to row 2, and that's going to be my new row 2. So I'm going to write that. That's my row operation, and then I'm going to write the result of that. So the result of that is that row 1 doesn't change. And you might say, well, yes, it did. You just multiplied it by a negative. The only change that occurred is in row 2. So row 1 is x minus y minus z is equal to 0. And row 3 is still 2x minus z is equal to 5. Row 2 is the only one changing. And to change it, I'm going to think about taking the negative value of row 1 and adding it to row 2. So you're going to end up doing a lot of mental math here, and I encourage you to just embrace that mental math. So if you need to write those negatives or change all of those signs, you're welcome to do that. Negative x plus x gives me 0x, that's what I wanted. Positive y plus 2y gives me 3y. Positive z and minus z gives me 0z, so write a 0 if you'd like. 0 plus 6 is 6. So that's my first row operation. Now, for my next row operation, I'm using this system of equations. So I'm no longer using these rows. This is my new row 1, row 2, and row 3. Now, so first step is done. The next step says eliminate the x variable in equation 3. Again, we need to get the only x should be in row 1. I need to then get rid of 2x. Well, how do I get rid of 2x? I'm going to add a negative 2x to it. So again, when you're doing step 2, you're going to be looking at row 1 and row 3. So I would take negative 2 times row 1 and add it to row 3 to be my new row 3. So again, nothing happened to row 1. So I'm rewriting it. Nothing happened to row 2. Row 3 is the only thing that's going to change. And again, embrace that mental math. Take negative 2 times this row and add it to row 3. So negative 2 times x is negative 2x plus positive 2x is 0x. So that's what I wanted is 0x. Negative 2 times negative y gives me plus 2y. I add it to 0y's, so now I have 2y. And negative 2 times negative z is plus 2z. So plus 2z minus z gives me plus 1z. And then I have 0 plus 5 is 5. From here, I've now completed step 2. Step 3 is to eliminate the y variable in equation 3. But before I do that, it makes sense to me that I'm going to go ahead and make the leading coefficient in equation 2 1. That's one of those optional steps that we might have to do. So before I do any rewriting of equation 3 again, I'm going to say, let's take 1/3, oops, I think I switched to blues there. Let's try again. I'm going to take 1/3 of row 2 to be my new row 2. So that means the first equation stays the same. And yes, you do have to rewrite the equations over and over. I'm taking 1/3 of 3y, which is 1y, and 1/3 of 6, which is 2, and nothing happened to my third equation. Now, did I have to do it in that order? No, but otherwise I was going to have to deal with some fraction here to make 3 turn into -2. So it made sense to go ahead and make the leading coefficient in equation 2 equal to 1. Now I want to eliminate the y variable in equation 3. So this is the y variable in equation 3. It's +2. I'm going to have to add -2y to it. So again, it makes sense that I would take -2 times row 2 to add to row 3 to be my new row 3. Again, so often, or all the time really, you're going to be looking at row 2 and row 3. Now, why would I not want to use row 1? So if I used row 1, I would only have to multiply it by 2, but look what would happen. 2x plus 0x would now give me 2x down here in row 3, and I don't want any x's in row 3. So it doesn't make sense to go back to row 1. You use that for step 1 and step 2, and then you switch to row 2. So let's take a look. I've got -2 row 2 plus row 3 is my new row 3. That means the only thing changing is row 3. Everything else stays the same. And now I'm taking -2 times y is -2y. Adding it to +2y gives me 0y's. I've got -2 times 0z, and adding it to z, which gives me z. And then I've got -2 times 2, which is -4, plus 5 is 1. So if we are only asked to rewrite in row echelon form, we are done. We can see that this is row echelon form. Sorry, I shouldn't have included that row operation. This is row echelon form, which is great. But now let's go ahead and do step 4, just for good practice for solving the equation. So if I were only asked to rewrite in row echelon form, I would stop right here. I'm done. But now they're asking me to solve. So use back substitution to solve the system. Again, we're going to have 3 values, an x, a y, and a z. Keep in mind that could be x1, y1, x1, x2, x3 instead of x, y, z, and it would be the same process. So I know that z is equal to 1 because that's my third equation. And I don't even have to back substitute to find that y is equal to 2 because that just happened. So finally, I'm just going to take x minus y minus z is equal to 0. And I'm going to replace y with 2 and z with 1. So I have x minus 2 minus 1, or x minus 3 is equal to 0. Add 3 to each side, x is equal to 3. So my solution is 3, 2, 1. Let's use the same process to rewrite this system in row echelon form. So to begin, my first step is always to eliminate the x variable in equation 2, unless of course I have to do one of the optional steps down here, which I don't seem to right now. And I don't have to do step 1 because, as you can see, I already have 0x in row 2. So that's good. So I'm going to start with step 2, which says eliminate the x variable in equation 3. So it seems that because I have a 1x and a -1x, that all I have to do is add those two rows together. So row 1 plus row 3 is going to be my new row 3, and my resulting system is x plus y minus 3z is equal to -1, y minus z is equal to 0, and now I'm going to add those row 1 and row 3 together. So x plus negative x is 0x, 1y plus 2y is 3y, and negative 3z plus 0z is negative 3z is equal to -1 plus 1 is 0. That's my first step. My second step is to eliminate the y variable in equation 3. Now, if I wanted to, I could go ahead and divide or multiply by 1/3, but let's go ahead and see what happens when I do step 3. I'm trying to eliminate the y. So this is a 3y. It makes sense I'm going to take this second equation times -3 so that I end up with -3y and plus 3y. So my new row operation is negative 3 times row 2 plus row 3 is my new row 3. That's going to give me the same row 1, the same row 2, and row 3, I'm now taking -3 times y, which is -3y, plus 3y gives me 0y. I have -3 times -z gives me positive 3z, minus 3z gives me 0z, so now I have 0, and then I have 0 plus 0 is 0. So this is the first time we've had this, all of the 0 rows are at the end. So this is in row echelon form. If they said rewrite in row echelon form and don't solve, I'm done, just like that. But let's go ahead and solve it just for good practice. We have talked before about solving parametrically. So what this tells us is that we have a free variable of z. So z is free. What that means is we're essentially making up a value for z, and then we're going to have the other values dependent on that. But again, we're going to make it parametric. So because z is free, we're going to say let z equals t. Now, we're going to solve everything in terms of z/t. So how do I do that? Well, if z is t, I have y minus t is equal to 0. So let's add t to each side. Y is equal to t. So z is equal to t, y is equal to t. Let's look at x. For x, we have x plus y minus 3z is equal to -1. X plus y is t, minus 3 times z is t. So I have x plus, minus, I have plus 1t and minus 3t, so minus 2t is equal to -1. And then I'm adding 2t to each side, so I have -1 plus 2t. So what is my final solution? My final solution is the ordered triple. X is -1 plus 2t. Y is t. Z is t. Which means I've solved this parametrically. To find solutions to the system, I'm simply going to vary t. So if I plugged in, say, t is 0, then that would give me -1 plus 0, which is -1, comma 0, comma 0. So that's one of the points on this solution. Let's let t be 1. -1 plus 2 would give me +1, and then t is 1 and t is 1. Let's let t be 2. -1 plus 4 would be 3, and then comma 2, comma 2. So these are all points on the solution to this system. I would like for you to try this question on your own, so when you're ready, press play to see how you did. In this case, the first step I would do is not step 1. We can see that I have a 3x, and if I tried to use scaling to multiply by 1/3, I would end up with a fraction and a fraction and a fraction. And fractions aren't fun most of the time. So instead, I'm going to use my first step to swap the equation to make equation include 1x. So I'm just going to swap row 1 and row 2. And remember, that's that equal sign with the arrow on each end. Row 1 and row 2 will swap. And that's going to make me happy because that gives me my first row as x plus y minus 2z is equal to 3. So I have just one x up there and I don't have to deal with fractions. This is now 3x minus 2y plus 4z is equal to 1. And then nothing happened to row 3. Now I'm going to do step 1, which is to eliminate the x variable in equation 2. So again, I'm focusing on x and 3x, which means I'm going to need a -3 times my row 1 to add to row 2 to get my new row 2. So that means my first equation stays the same. My second equation is -3 times x, which is -3x, plus 3x, which is 0x, no x's. -3 times y is -3y, minus 2y is -5y. And -3 times -2z is positive 6z, plus 4z is positive 10z. -3 times positive 3 is -9, plus positive 1 is -8. Nothing happened to row 3. Next, I'm going to eliminate the x variable in equation 3. So again, I'm looking at x and 2x, which means I'll have to take row 1 times -2. So -2 row 1 plus row 3 is my new row 3. Let's see the result. Oh, that was awful. Row 1 is still x plus y minus 2z is equal to 3. Row 2 is still -5y plus 10z is equal to -8. And row 3 is now -2 times row 1 plus row 3. So -2 times x is -2x plus 2x gives me 0, 0 x's. -2 times y is -2y, minus 3y is -5y. -2 times -2z is positive 4z, plus 6z is positive 10z. And then -2 times 3 is -6, plus 8 is positive 2. So you might be looking at this and saying, well, I see that there's a problem. But if you didn't, that's okay. We're going to go ahead and continue to make it very clear exactly what's going on. Step 3 is to eliminate the y variable in equation 3. That seems to be pretty easy to do because I have -5 and -5. So all I need to do is take a negative row 2 and add it to row 3 to be my new row 3. So row 1 is still x plus y minus 2z is equal to 3. Row 2 is still -5y plus 10z is equal to -8. And row 3 is -5y, so positive 5y minus 5y is 0y. And -10z plus 10z is 0z. So I actually have a 0 on the left hand like I did on our last question. But on the right side, -8, so positive 8 plus 2 is 10, and I have 0 is equal to 10. 0 does not equal 10. So because I don't have an all 0 row, I have 0 is equal to 10, which is false. Because it's false, this is a no solution. So there's no solution to this system of equations. If we were only asked to write in row echelon form, we would stop right here as well, and we just wouldn't say that there's no solution. Up next, we're going to take a look at Gaussian and Gauss-Jordan elimination.